All right, welcome to office hours, and let's see, we'll do a dynamics problem in this one. And in this problem, let's see, we got some crazy looking thing given. Let me see here. It looks like, we have a particle or an object with a mass of 400 kilograms, and it's pulling up on a pulley system deal. Oh my gosh. Okay, so here's what it looks like. And anyway, what we need to do is find, in this problem, it'll become more clear when I can draw the schematic. It'll be find the velocity. Find the velocity at t equals 2 seconds. The system looks like this. There's like a table, or here there's a schematic. And in this schematic, I have a table. Where's my straight edge? All right, so it's like a corner. And then off that corner, there's a pulley. And then over here, there's a motor. I put a motor right there. And then there's a rope. This goes down like that. Yeah. And then there's another little pulley here. And there's a crate at the bottom of this, like this, and that crate is what weighs 500 or 400 kilograms. Yes. All right. And this is a motor. Okay, so this is a motor. And and there's a force, a graph also that's given, a graph of the force in the motor as a function of time. And it looks like it's a parabola like this. And it has a function here. F as a function of time is 625 t squared. And the units output is in newtons. So this force is in newtons. Newtons, and the time is in seconds. All right. And at 2 seconds... At 2 seconds, if I plug in 625 times 4 is 2,500 newtons. All right, at 2 seconds. All right, great. So what do I need to do in this problem? Well, the force increases from 0 to 2,500 newtons in 2 seconds. Okay, and I have to determine the velocity of the crate at A. So right when it starts lifting off the ground, I need the velocity, right? Mm-hmm. And so what I need in this problem is the force at which it starts to lift off the ground, okay? Which really means a static case, okay? Mm-hmm. And then that instant the crate just starts to lift off the ground, that'll be the force in the rope. And then I have to apply that force in a dynamic case. Mm-hmm. All right, good. So let's start with the static case to see what the force in the rope will be, which I think it'll be pretty obvious. Mm-hmm. But we'll call it the static case. And I guess I have a couple choices. Oh snap! The motor is here, right? And I could do a free body diagram of, it depends what I want to do the free body diagram of, right? Mm-hmm. But I want to know what the force is that the motor needs to deliver. And because it's in a pulley system, mm-hmm. It's different than the force that's in the weight of the particle itself. So really, again, we're assuming that all the pulleys are massless. So essentially what I have is this, I shortened the cable, and then I have this free body diagram, and because a pulley's massless, I can make this cut there. I'm cutting here and here like this, and there would be a force. I'll call this the force in the rope. I'll call that T, mm-hmm. And I would have the weight here. I'll call it W, and which way do you want to say is positive, up or down?
We could say. I guess we'll do, I guess just because it's a pulley, we could say down is positive.
Okay, down is actually convenient for us later, but we'll say here, this is positive y, and then positive x would be to the right. And And then here, this, because it's a static case, everything equals 0, right? So by equilibrium, now I'm going to apply my equilibrium equation. Some of the forces in the vertical, positive is downwards. I'm looking at the static case, so I'd have negative 2t plus the weight equals 0, and that tells me the force that I need in the rope, the tension force, is W over 2, which would be 400 kilograms times 9.81 meters per second squared divided by 2. And that would be 200 times 9.81, which is, was it
196.2.
1960, 196, are you sure? Is it 1,962?
No, just 196.
400 divided by 2 times 9.81. I got 1962 newtons.
Oh, I put 40, not 40.
Oh, okay. So 1962 newtons is the force that I need in the cable, and that looks good. Okay, all right. And what else do I need? I need yeah, I think that's it. 1962 newtons, and okay. I get it. This problem now. Okay, so this 1962 newtons is actually right here, the time in which that occurs. The time at which this occurs. Time at 1962 newtons, if you will, or F equals 1962 newtons. That force that the motor is going to deliver to the rope will be, I just take the relationship here, 1962 newtons is equal to 625 times t squared, right here, and that would be, t is, the 625 has units of Newton per second squared, but it's all good. 1962 divided by 625, and then the square root of that is 1.77 seconds. 1.77 seconds. So 1.77 seconds. Okay, so that's the time at which the cable or the crate starts to move. Right here. This would be 1.77 seconds. Right here. This is 1962. Okay. Shoot. Now what do we need to do? We need to find the velocity at 2 seconds. Okay. So at this case, at 1.77 seconds, the velocity is 0. Okay. The velocity is 0 there at that point. All right. And let's see here. Oh, what would the velocity of the... Can we determine the... Oh my gosh. I suspect we're going to need a cable length equation, right? And so I'm going to pick a point here to describe the motor M, and then I have the crate A here, okay? And I have to... So here, I'll call this number 3. I'll get a cable length equation. 1, 2, 3. Cable length equation. And in this, because we have a pulley problem, I need to choose a fixed location. So here, I'll choose a motor as a fixed location to M. I'll call that plus SM, that distance. And then from the pulley here to the cable at A, I'll just say this is part of the cable at A because that, so I'll call this plus SA. And that would tell me, let's see, ooh, interesting. The length of my cable, the one thing I also need is the length here from fixed point to fixed point. I'll call that L, okay? And the length of the cable I'm interested in is this orange part. Here, I'll use green or red. It would be this plus this. These would be, that red distance would be the cable length that I'm interested in. And this first portion right here is L minus SA, based on the way I chose my reference. I'm sorry, SM, L minus SM, plus 2SA equals 0. And that would tell me, if I take time derivatives, it would tell me minus Vm plus 2 Va equals 0. And then it would also tell me, I could also get acceleration. This would be telling me minus Am plus 2Aa equals 0. Yeah. Mm-hmm. I would have those relationships. All right. Wow. Okay. Huh. Interesting. Okay. All right. Man. This is interesting. This is very interesting. All right. So now I want to look at the dynamic case. Okay. So of particle A. So 1, 2, 3. Is this 3? 3, 4. 4. Let's call this 4. The dynamic case. Dynamic. So it's going to start moving. Okay. And man, I think I'm probably going to need this as a function of time, right? Mm-hmm. Okay, so here in my dynamic case, again, I'm drawing the same free body diagram as I did earlier. This thing right here. Mm-hmm. I'm going to draw this, and then, but it's not going to be equal to 0. So here, I would have, here is the particle, here's the rope, here's the pulley, here's the cut face, boom. And this is the tension force, T. I think we've already established that T equals F, right? Mm-hmm. We've pretty much established that. But this is T. And I would have a weight, W. And thankfully, because, it was important, if we go back here, it was important that we chose positive SA as downwards, mm-hmm. because we want to be consistent with the direction of positive motion in our static, or in our force, in our equation of motion. So here, this will be plus y is positive downwards again. And this time, this does not equal 0. This is 1D motion. Here's the pulley. Here's the mass. And I will have an inertial term, at least in the vertical direction. And I will call that MA. It would be MAY, but this is particle A. It's only moving in one direction, so I can call it MAA, okay? Because there's no horizontal motion here, and and so the equilibrium, or the equation of motion that's relevant for me here, the EOM, would be sum of the forces downward, right here, is equal to 0, and I'm going to apply F equals MA. And again, that's just going to be negative 2t plus W equals MAA, like this, okay? And what I have is that T is equal to F, and it's a function. And so here, this would be negative 2 times, what was it, 625 T squared? Negative 2 times 625 newtons per second squared. I'm going to put the units there. Newtons per second squared times T squared plus the weight of the crate is equal to, here, in fact, forget the weight of the crate. I'm going to write that as mg, all right, the mass times gravity, is equal to mass times the acceleration of A. Yeah? And what this tells me is that the acceleration of A is negative 2 over m, the mass, 625 newtons per second squared, times t squared, plus g. Yeah? And that means I have acceleration as a function of time. I've created an equation for acceleration as a function of time. So if I plug in some numbers,
Wait, shouldn't the parentheses, or I guess never mind. I guess they don't necessarily have to.
Oh, no. Yeah, so here, acceleration of A as a function of time is going to be, let's see, let me make sure the units work out. Negative 2 over m, and mass was it 400 kilograms?
Yes.
So here, 4 400 kilograms times 625 kilogram meters per second squared divided by second squared times time squared plus 9.81 meters per second squared. And the kilogram units cancel here. That's convenient. And what I'm left with is that this function is AA is equal to, let me do some quick calculation, 1250 divided by 400. It would be negative 3.125 meters per second to the fourth times t squared plus 9.81 meters per second squared. Yes. Okay. That's pretty good, right? Mm-hmm. Okay. And so that means I have the acceleration as a function of time for the particle at A. Right? Mm-hmm. Okay. And I also know from now I have 1D motion, so now I can look at the kinematic case. 5 kinematics, and this is 1D motion. Particle A is just moving in 1D motion, motion here. Okay, and I guess technically speaking, I have the acceleration of the motor as well, mm-hmm. right? So I have lots of choices. I could do my 1D motion with A, or I can solve for AM mm-hmm. as a function of time and do my 1D motion on M. Mm-hmm. Does that, yeah?
Yeah.
Yeah. So I don't know, which way do you feel better? You want to do the 1D motion on M or on A?
I guess just on A.
On A. So we want to find the velocity. Yes, we'll do it on A because we want the velocity
We want
of A.
the velocity of A.
Oh, okay. So we might not even need the cable length equation. Huh, that's convenient. So here, if I look, let's do the 1D motion on A. So on A, so here I know the acceleration of A is a function of time. So AA. And I know that the acceleration is related to dv dt, like this. And so then I just set that equal to, this negative 3.125 meters per second squared, to the fourth, times t squared plus 9.81 meters per second squared. I'm going to set up the integral, which will be, what a waste of time there, but it's all good. The integral will be, I'll have to write this again one more time, 3.5 meters per second to the fourth times t squared plus 9.81 meters per second squared dt equals dv.
Wait, where did you get this number?
Which one?
The 3.125?
That negative 3.125, I multiplied 2 times 625 divided by 400.
Oh, wait. Yeah, I did 5 by mistake.
Oh, okay, no problem. Okay, and now to get the actual velocity at 2 seconds, let's see, at time t equals, so this was important for me because at time t equals 1.77 seconds is when I start moving. 1.77 seconds is my lower bound of this integral, and at that case my velocity is 0, right? And then I want to find the velocity at 2 seconds, right there. I could find the velocity as a function of time too, mm-hmm. but in this case I can go directly to the answer. So velocity at 2 seconds, and so now I integrate and solve with these bounds, and so this would be negative 3.125 meters to second to the fourth over 3 t cubed plus 9.81 meters per second squared times t, all evaluated from 1.77 seconds to 2 seconds equals v. Minus 0 technically, but that's all good. We don't need that. So v at 2 seconds, at t equals 2 seconds. And that will be some numbers. Let's see. Okay. Put parentheses around this minus the whole thing again. Minus 3.125 over 3 times 1.77 cubed plus 9.81 times 1.77, and this will be my answer at t equals 2 seconds, and my velocity at t equals 2 seconds. What'd you get?
I got negative 0.301.
Oh crap!
Which is where I don't know.
That doesn't seem well. Negative. Actually, it could. Well, no.
Yeah, negative in this case. Well, no, doesn't.
Oh
it imply
yeah,
that it's
negative.
moving up?
Yeah. Oh
So
yeah,
it's
yeah,
the
yeah,
line.
yeah. That's right. Because it's moving up. Yes, and so that would be like we said, positive is moving down, so it's moving up. Yeah, so that actually negative would make sense. And in this case, here, let's see. I'll double check too. Oops. So I got this. I got a. Is this right? I got 11.29 meters per second minus. Let's see.
Hello? Did you call me? Yeah, are you?
Minus 11.59.
You're already in? How much are they?
0.297? 0.3?
I got 0.3.
Okay, so this I got 0.297, negative 0.297 meters per second, which just means that this is 0.297 meters per second upward. All right, hopefully that's right.
Why do you buy so many?
All right, and that will be the velocity of the crate. I could even determine the speed of the motor using the cable length equation, but we didn't even have to use the cable length equation. My instinct always is when I see a pulley system that I might need the cable length equation. Might as well just set it up, but it's interesting that we didn't need it this time. All right. Hopefully that was helpful. I'll see you later.
Thank you.
Bye.